Okay, so let's get started. Like I promised, what we're going to do is we're going to start. By the way, I do have lecture notes. I don't think I mentioned this. I do have lecture notes for this course, and they're full of little grammatical mistakes and typos. Feel free to let me know. They're called Brad Algebra notes. They're posted on my webpage. They're posted on the Canvas page. We are starting on Chapter 6 modules. That's page 79. Now, how many of you have encountered modules in a previous incarnation of an algebra class before? Not ever. How many of you have encountered vector spaces? Right? So that's linear algebra stuff. How many of you know what an abelian group is? Right? Well, this modules basically function to generalize both vector spaces and abelian groups. They come up all over the place in mathematics, and modules are a natural generalization. Of course, right before the person gets here, right? Modules are a natural generalization of vector spaces and abelian groups, and we'll see this. So basically, what a module is, what's a vector space, right? When you take linear algebra, how many of you took a linear algebra course early on in your career, like sophomore, maybe, right? And what do they do with a vector space? They list, I mean, it's really obnoxious because they list like 12 things, right? Two vectors, v plus w equals w plus v, and then they go through all this business about v plus w plus u equals v plus w plus u. They go through the associativity and all this bit long thing. Well, maybe you came to realize that really what a vector space is an abelian group, right? That's what the vectors are. And there's just one other kind of operation you can do, and that's kind of scalar multiplication, right? So when you have a vector space over the reals, for example, what can you do with vectors? You can add them, you can subtract them. There's a zero vector. The addition is nice. That is, it's commutative, it's associative. And you've got this other kind of magic thing you can do. You can multiply by scalars from the reals. When you take a real number times a vector, what you get is a vector. So let's kind of start off here. I'm going to start talking about left and maybe right arm modules, and I will probably discard that fairly soon, but I'll just want to point out that this thing exists. First day, chapter 6. It's like going to a Star Wars movie, isn't it? Definitely. 6.1.1. A left arm module. We'll call it M. So a left arm module, which I'm going to call M, is just an abelian group. Okay, so this should be a familiar old friend, equipped with a function R cross M to M. This is just a fancy way of saying our scalar multiplication, right? So we're going to write the order pair Rm as Rm. So this is kind of a fancy way to say multiply R times M, and it's still an element of M. This is the analog of what you're used to with scalar multiplication from a vector space, such that for all A, B, and M, and RS and R, we satisfy a few things. One, So the scalar multiplication, if you will, plays nice with the addition in the sense that R times A plus B, sorry, it's RB. 2, it plays nice both ways. The addition in the ring distributes. Whoops. Did that one, didn't I? All right, let's say. There we go. And we do have a multiplication in R because it's a ring. So I've got to know how that plays out with this. Notice, of course, SA is an element of the module because it's scalar multiplication. So RS times A is R times SA. So this is what it means to be an R module, right? It's just an abelian group that has this scalar multiplication that plays nice with the multiplication and addition from R. Now, I'm going to add another caveat. If R is a ring that has an identity, right, which most of my rings do, and when I multiply 1 times any element of when I multiply 1 times any element of the module, I still get that same module. We say M is a unitary R module. And this will be my default. When I say a module, if I don't specify, you can assume that it's a unitary unless I tell you it's not necessarily unitary. Notice, by the way, back in the day, when you had vector spaces in linear algebra, this was probably one of the list of 45 little axioms they had, that when you take 1 times any vector, it's equal to that vector. So in vector spaces, this is the default assumption. If R is a division ring, by the way, does anybody remember what a division ring is? Okay, means the non-zero elements of R are invertible. So in other words, the non-zero elements of R form a group under multiplication, right? So for example, any field is a division ring, right? But there are, of course, non-commutative division rings as well. Then we call this M is called left vector space. So basically, the definition we're taking here is that a vector space is just a module over a field. Or I'm sorry, well, more generally a division ring, I should say. So here's an exercise. This is just kind of a little fun thing to do. Pick your favorite R module. Show of course, the module is an abelian group, so it has a 0 element, right? So take the 0 element of the abelian group and multiply by any element of the R, and you get. And also, of course, the ring has a 0 element. So that is, if you take any element of the ring in a module and you multiply it by the zero element of the module, you get the zero element of the module. And if you take the zero element of the ring and multiply by any element of the module, you get the zero element of the module. See if you can prove that. Okay, so examples. Any questions? I'm real big on examples. So let's take a look at a few. Okay, suppose I have any abelian group on the planet or off the planet even. Let it be any abelian group that you want. Then A is a Z module, where Z is the ordinary integers. Right? And let me tell you how that module structure works. I've got to tell you how the scalar multiplication works, right? So I don't know if I'm going to do both A and B, but we'll see. If M is greater than 0, and it's an integer, then M times A, how do you suppose you define this? That's right, just add A to itself n times. So what's a natural way? What if n is less than 0? Right, exactly. Add negative A to itself, the absolute value of n times, and of course, about that 1, 0 times A, 0, the element that we're going to emphasize 0 in the given group. And so this is why one of the things that I said that modules are a generalization of abelian groups, because any abelian group, no matter what it is a module for the ring Z. Right. So for example, Z mod 2Z, Z mod 6Z, the rational numbers, the real numbers, all these are abelian groups. They're all Z modules, just under this particular definition of how the multiplication works, or the scale of multiplication. Here's an example. Let funny look and see here be the set of all functions from 0, 1, the interval 0, 1 into reals that are continuous. Right? This is an abelian group. In fact, that's probably one of the things you learned in calculus, even though they didn't tell you that, is when you add two continuous functions, it's continuous function, you subtract it, and so forth. So this is actually an abelian group. So it's a Z module, but this is also a module over the reals, where the scalar, where multiplication by a real number times f, the new function rf is r times f of x, and so this is an R vector space. By the way, this is a freaking humongous vector space. It is very, very big. The set of continuous functions from 0, 1 into R, very big vector space. But I can tell you this, so this is kind of a spoiler ahead. As a vector space, C is isomorphic some number of copies of R. This index set, the number of copies will be very, very big. Right? I want to tell you, Bill, how many of you have seen this notation with abelian groups, the direct sum? The continuous functions from 0, 1 into R as a vector space over R, that is a direct sum of a whole bunch of copies of R. Probably a lot, but I find that sort of comforting that it reduces to something so simple. All you need to do is know the size of the index set. If R is any ring let's see here. Yeah, R is a ring and I is a left ideal of R. Then I is a left R module. And it's easy to verify that it works because if R and S are in R and alpha and beta are in the left ideal, then R times alpha because a left ideal sucks, it's like a vacuum cleaner, it sucks all this multiplication from R into the ideal itself. And we've only got those three axes to satisfy, and it's easy to check if these all work, right? So any left ideal is an R module. Here's another one. If R is a ring and I in R is an ideal, this time a two-sided ideal, then R mod I is an R module. Right, and the multiplication looks like this: R times alpha plus I. So here's your scalar from R. Here's your element of R mod I. And your output is an element of R mod I. So that's another source. I'll give you a couple more examples. If R is well, if R besides T are both rings, then T is an R module. Because if you multiply an element of R times an element of T, then RT, because you have this containment here, is an element of T. And again, you can check module axioms. So I think these examples might paint a picture of the importance of modules, right? Because what do we see here? An ideal in a ring is an R module. A quotient of R by I is an R module. If you have R is contained in a bigger ring is an R module. So they're all over the place, right? I mean, this thing isn't an ideal. This thing, R mod I, is generally not a subring of R, but modules kind of unify all this. So you have all these things that are R modules. Let me give you one kind of final sort of exotic example, if you will, and we're going to come back and go over this example in depth. There's a kind of a final example. So we're going to actually later in the course, we're going to actually look at this more in depth because this is the idea behind canonical form matrices. Let F be a field and B a vector space. So I'm writing this a little bit generally, but you might picture F to be real, say, and V to be just, you know, R2 or something like that. I need another player here. Information. So for example, so T is a linear transformation. So you get a field, vector space, a linear transformation from the vector space to itself. So for example, if this is finite dimensional vector space over a field, you can sort of realize T is a matrix, can't you? Then V we can make V a module. Yeah. I know it's a vector space. It's a module over R. But I'm sorry, it's a module over F field, right? Because it's a vector space. But I'm gonna make it a module over something else. I'm gonna make V, the vector space over F, a module over the polynomial ring. And here's the way I'm going to do this. So let F of X be a polynomial over the field and V in the vector space. Any ideas how I might do this? So I need to take a polynomial and multiply it by a vector, and it needs to kind of barf out a vector, another vector. Yeah.
Are you going to plug in the linear transformation into polynomial?
Very good. Plug in the transformation polynomial, right? And that gives you a new transformation, and then let that act on V. And because this again is a linear transformation from V to V, so when it acts on V, it gives you a V. You might check just for giggles that the axioms for module work here, but they do, and we're going to look at this one actually later. Okay. Any questions so far? Actually, I lied a little bit. I'm if R is a ring, let's say, because I don't want to worry about left or right here. In fact, usually you can, if I use the word ring, later in the course at least, I will refer to a community. Then notice that the direct sum of R and the direct product of R over any index set for both R modules. You can consider this to be a special case of this, because R itself can be identified with subrings of this as well. Just to make sure you all know the distinction between the direct sum and the direct product here. Right. This is just nest, that is sort of generalizations of sequences with terms in R. And this, the difference here is this is a this is a subgroup, we'll say, where almost every entry is zero. And by almost every entry, I mean all the finite entries. I'm sorry about this. I'm gonna go complain and we'll get this taken care of, hopefully by next time. Notice that in both cases, let's see, sequence. Notice if you have, I shouldn't say sequence, I'll say net. The reason I shouldn't say sequence is because this may not be a countable set. Then R times your net. Okay. Well, when you did vector spaces back in the day, right? Somebody tells you what vector space is, but it's examples. Then what's the next thing you look at, right? After you look at vector spaces, you look at linear transformations, right? Because almost always focus for first linear algebra class might be on the matrices. And so we want to generalize the notion of linear transformations to modules. Let me point out that this also generalizes abelian group homomorphisms. Right? Again, modules are generalizations of vector spaces, and they're generalizations of abelian group or abelian groups. And so this is generalized both of these. So let me give it to you. Definition. 613, let A and B be R modules. And F a function from A to B. We say that F is an R module homomorphism. Yeah. Got a couple of things that won't happen. First, I want F of A1 plus A2 to be F of A1 plus F of A2, right? This is the first thing. This is exactly what you had when you had the definition of linear transformation, right? And of course, you probably didn't hear this in your first linear algebra class, but I could have, instead of writing all that garbage, I could have just said F should be a homomorphism of abelian groups, because that's all that means right there. What else do I need? What I need for an R module homomorphism, just like any homomorphism type thing, I want it to play nicely with all the operations. So I've kind of got the addition covered here. I want it to play nice with the scalars. And so there you go. Let me make a note. If R is divisionary, then F is called a linear transformation. And if you look back in your old linear algebra text, this is exactly what you need. These are exactly the assumptions made for a linear transformation. It also generalizes abelian groups because, well, really, the first axiom there is what you need for abelian groups. Okay, this is something that you might have seen in linear algebra class as well. Limit 614. Let phi from M to N be an R module or be a function, right? Here, M and N are R modules. Like that, you know, then phi is an R module homomorphism. If and only if phi of M1 plus RM2 is equal to phi of M1 plus RP of M2. For all M1, M2, and M and R and R. This is kind of a shortcut. This sort of collapses these two things into one step. Notice that it's you sort of do the addition here and then pull the R out for the scalar multiplication here. Again, the proof of this is pretty routine. How many of you have seen this in linear algebra course? I think a lot of times they'll give you that little shortcut in a linear algebra course as well. Note, let me make a mark here. Let's take a look at this right here. This means an abelian group homomorphism, right? And this means that you can pull the scalars out, right? Notice if your ring is Z, then this means if R is, for example, a positive or negative integer, this just means you can pull this out. So my remark here is Z module homomorphism is synonymous with abelian group homomorphism. Right. And this kind of goes hand in hand with that statement I made that any abelian group is a Z module. Do not confuse ring homomorphism and ring homomorphism means that f of R A, R and A both being on the ring, is f of R F A. R module homomorphism means you can just kind of pull that R out. And these are usually very different. Let me give you an example. Consider Fn from Z to Z. So I'm going to give you kind of a simple function. The n is supposed to be suggestive in the sense that Fnx is in x. So basically the function Fn just means take whatever the input is and multiply by n. For all n in Z, this is a Z module homomorphism. But it's usually not a ring homomorphism. By the way, for what values then is that a ring homomorphism? That's right. Well, actually, I sort of asked you a trick question. If n is 1, it's certainly a ring homomorphism, right? Because it's the identity function. I agree with that. 0 is arguable in the following sense. If n is 0, then this is the function that takes everything to 0. Now it depends on who you're talking to. Some people define a ring homomorphism to have to take the identity of the ring to the identity of the ring, in which case this wouldn't be. So from a strictly definition point of view, this when n equals 0, this would be, right? But if you also want to demand, which many people do, that the identity goes to the identity, then this only works for n equals 1, actually. So, but I'm not going to argue those semantics here. Here's another one. It's not a ring homomorphism. Example. Where R (1) defines F from the polynomial ring by F P of X is X P of X. Notice this just takes any polynomial, multiplies it by the scalar X. The scalar from the ring. Here, right. So let's go through this. Let me verify this here. So checks out as an abelian group homomorphism. Make sure I've got the field right here. And here I'm going to take R to be, this is modulo over Rx. So let's have F of R times P of X. This is X R P of X, which is R X, which is R F P of X. So here I'm treating Rx as an R module. This also works more generally. Let me point out also, when I have R module homomorphisms, I sometimes add little adjectives to them, right? Like if I say an R module epimorphism, this means an R module homomorphism is onto. If I say an R module monomorphism, it means It's 1-to-1. If I say an R module isomorphism, it means R module homomorphism. It's both 1-to-1 and onto. Let me give you kind of a little proposition here that also introduces some notation. Let M and N be R modules. I am going to define the set How many of you have ever seen this notation? Okay. If you have, let me tell you what it means. Hom means homomorphism. The sub R means R module homomorphism. So this is the collection of phi function from M to N, such that phi is an R module homomorphism. So I'm making another structure out of, I'm looking at all homomorphisms from M to N, R module homomorphisms. This is an abelian group. Hom R M N is an abelian group under pointwise multiplication, or I'm sorry, pointwise addition of functions. Additionally, if R is commutative, then it's an R module. So I point out in the first case that R doesn't have to be a commutative ring. Like I said, later in the course, my default will be that rings will be commutative. But my super default will be rings have identity. I will point it out very carefully if I'm not assuming that rings have identity. So we're out of time for today. To see if you can figure out why this is true, and we'll pick it up there next time. Anybody got any questions? Any questions? Okay, you can look. I'm going to make your homework live on Canvas, but remind me if I forget on this day. On Friday, remind me and I'll say a few words about the problems. Y'all have a good one, and we'll see you next time.
Division T is a negative domain or not.
Okay, I'm sorry. So what about the?
When you talk about division ring, is it a negative domain or not?
Not necessarily. So when I say a division ring, if the division ring is commutative, then it's a phi, right? If it's not commutative, well, then it's a non-commutative division ring. A division ring will have no zero divisors, right? Right? Because every element that's not zero is invertible, right? So for example, have you ever looked at the quaternions?
Yes.
Okay, that's an example of a division ring. You can also take all fractions of polynomials and two or more non-commuting variables. That's another way to make a division ring. It's not a right. So for